Hello friends, this is Priyanka. Today we are going to solve a problem for given mechanism. In this video we are going to study how to draw velocity diagram and acceleration diagram for the given mechanism. And most important thing is that we are going to learn in which direction we have to take the velocity vector as well as acceleration vector and how to choose the direction of radial and tangential component of acceleration. So this point of view, the video is so much important, so please watch this video till end and please note down the important points about the direction of the velocity vector and the acceleration components. Now first I will read what is the given problem. In the mechanism as shown in diagram, the slider C is moving to the right with a velocity of 1 meter per second and an acceleration of 2.5 meter per second square. The dimensions of various links are AB is equal to 3 meter inclined at 45 degree with the vertical and BC is equal to 1.5 meter inclined at 45 degree with the horizontal. Determine the magnitude of vertical and horizontal component of acceleration of point B. Angular acceleration of the links AB and BC. So this was the given question. Now most important thing is that we have to draw first space diagram with some suitable scale. Now if we observe, there are two links, that is AB and BC, where AB is given 3 meter and BC is given 1.5 meter. So if we convert it into centimeter, then AB is equal to 300 centimeter and BC is equal to 150 centimeter. So we will use here scale 1:1/10. That is, for 300 centimeter we will use here 30 centimeter and for 150 centimeter we will use scale, that is 15 centimeter. Now first we have to draw one vertical line in the form of dash and dot. And on that line we will select one fixed point, that is the point A. Now the link AB is at 45 degree angle, so we have to take 45 degree angle and we have to take the dimension AB is equal to 30 centimeter. Now from this point B we have to draw one horizontal line and again we have to take 45 degree angle inclined with this horizontal line and again we have to draw BC is equal to 15 centimeter. Now at the point C there is the slider and its motion is towards the right hand side direction, that is also mentioned in the question. So here we will draw the slider C and which is having motion towards the right hand side. So along the motion, that is the motion is in the horizontal direction, so we will make here one line in the form of dash and here with this vertical line there is the fixed point D. So we can say that the slider C is having the horizontal motion with respect to the fixed point D. So in this way this diagram is getting completed. Now we will move for the velocity diagram. So how to draw? So here it is given that the VC, that is the velocity of C with respect to this point D, fixed point D, is given 1 meter per second. Now it is also mentioned that this motion of the slider C is towards the right hand side. So we will take one scale and we will draw the velocity diagram. So I will take here scale, that is for 1 meter per second I will take here as a 15 centimeter. So here I will take one fixed point. So here if we observe this diagram, here is point A and point D. These 2 points are the fixed points. So I will plot here one fixed point, that is point A, D. That is, I will use the small letters for the velocity diagram. Now the motion of the slider is along the horizontal line, so I will take the line parallel to its motion, that is horizontal line. Now in which direction we have to take this line? So this direction is towards the right hand side, so I will take here the line towards the right hand side direction. So from the fixed point D to C, now scale is 1 meter per second is 15 centimeter. So I will use here as a distance equal to 15 centimeter and I will mark here one point. So here is the point C, here is the arrow. Now this vector DC indicates us the velocity of C with respect to D. So I will say that it is Vc. Now if we observe here, the slider C is connected to this link BC. So how to indicate the velocity for this link BC? So we know that the velocity, that is the linear velocity, is always in perpendicular direction with that link. So I will take here, or I will draw here one rough line with this link BC. So I will align this edge to the link BC, and from the other edge I will draw here one construction line, that is the perpendicular line in the form of dash. So this is the rough construction. So now we have to take the parallel line to this construction line, and here is the point C. So for this link BC I have to draw the line parallel to this line but passing through point C. Now currently I don't know in which direction we have to draw this line. So I will take this line parallel to this, and if I move this scale, and here I will draw line in both the direction. Now again in the same way, now this point B, or we can say fixed point A, here is the fixed point A. Now this point A is connected to this point B. So again, how to show this linear velocity for this link? So again I will draw here one perpendicular line. So I will align one edge of the protractor with that link, and from the other edge, this is the rough construction that we have to remove. Then again I will take here the line parallel to this line. Now if we observe this, here this is the line. Now if we observe on both sides of this point A, I have drawn the line. So here is the point of intersection. So this point of intersection is the point B, because A is the fixed point and here point C is already there. So here is the point B. So from the point C there is the direction that we have to give. The C is the initial point and B is the final point. And here also A is the fixed point. So from A towards B we have to show arrow. So in this way here is the velocity. Now how we can indicate this vector AB? So here I will say velocity of B with respect to fixed point A, that is VBA, or simply we can say VB. Now for this BC, how we can say that? So here velocity of this point B with respect to C, that is VBC. So this is the velocity diagram. So these extra lines we can remove here. Now we will measure the scale for this vector AB and CB, and we will convert it into the velocity so that we can find out the linear velocity. So if I convert this, what is its scale, that is AB, that we have to measure. That is 10.5. So I will take here vector AB. AB is equal to 10.5 centimeter. And in the same way, this vector BC is also 10.5 centimeter. Now we have to convert, because we have this scale, that is 1 meter per second is equal to 15 centimeter. So I will take here 10.5 centimeter. How many meter per second is there? So I will make here cross multiplication, that is 10.5 divided by 15. That is 0.7. So we can say that for this AB, that is VBA is equal to this VBC is equal to 0.7 meter per second. So this is the answer, that is this is the linear velocity. Now if we show this velocity, so how to show? So VBC, now we have to show this VBC, that is it is perpendicular in the perpendicular direction to this BC. So here is the link BC. So now its arrow is towards this upward direction. So if I take one line perpendicular to this link BC, and if I take here the arrow in the same direction, then here is the VBC. Now in the same way for VBA, so this is the perpendicular line. So I will extend here passing through this link AB, and now its arrow is towards the right hand side but in the upward direction. So here is the arrow. So this vector will indicate us VBA, or simply we can say VB, because A is the fixed point. So in this way, this velocity diagram with some suitable scale is getting completed, and with that scale we have calculated the velocity of the links. Now we will move to draw the acceleration diagram. But before that we will understand some basic concepts regarding acceleration. So here this acceleration is having two components, that is the radial component of acceleration and tangential component of acceleration. Now if we observe here, suppose we will consider xy is the link, then the radial component of acceleration, how we can indicate here, that is a raised to r xy, and how it is getting calculated, that is the linear velocity square for this link xy divided by the length of link xy, and we have to take this radial component parallel to the link xy. Now how to calculate the tangential component of this link? So a raised to txy, this is, in this way we have to denote that tangential component, which is equal to alpha, that is the angular acceleration alpha xy multiplied by the length of link xy. And how to show its direction? So it is in the perpendicular direction to the link xy. So now I will use the red marker to show the radial component and tangential component of the acceleration, because the combination of radial component and tangential component will give us the total acceleration. Now if we observe this diagram, if we observe here point A and point D, these 2 points are the fixed point. So I will take here one fixed point, that is for the acceleration I will take as a small letter and dash, that is A dash and D dash. Now it is given in the question that the slider C is having the motion towards the right hand side direction. So its motion is given, that is towards the right hand side direction, that's why acceleration is also in the same direction. But what about the magnitude? So in question it is mentioned that this acceleration for the slider C is 2.5 meters per second square. So this is the total acceleration given. So I will use the red marker and I will show this 2.5 meters per second square. So for that I have to decide some particular scale. So I will take here scale for 1 meter per second square, I will take 10 centimeter. So for 2.5 meter per second square, that is 2.5 multiplied by 10, that is 25 centimeters that we have to take. So from this A dash to D dash, now here slider is having reciprocating motion along this horizontal line. So we know that we have to transfer the motion of slider as it is. So I will transfer the motion that is in the horizontal direction as it is. Take here scale, that is 25 centimeter, and draw one horizontal line. Show here arrow also, here is the point C dash, and this vector D dash to C dash indicate us the acceleration of C. Now next, so for this point C, the link BC is getting attached. So for this link BC, we have linear velocity that we have calculated earlier. So from that we can calculate the radial component of acceleration. So here radial component of acceleration, that is ARBC, is equal to linear velocity of BC square divided by BC. So what is the linear velocity? That is 0.7 square divided by BC, that distance is given 1.5 meter. So when we calculate us, we will get here 0.32 meter per second square. Now we have to draw the radial component for this BC, and it is parallel to BC. So if we observe passing through this point C dash, I have to draw the parallel line. But in which direction I have to draw? Now if we observe here, this is the velocity of B with respect to C. That means the point B is moving with respect to point C. So I have to take the arrow in the downward direction. So we know that the fixed point or the other about which the velocity is there, that we have to take here the arrow in that direction. So this point B is moving with respect to point C. So downward direction. So I have to take this line parallel to this BC but in the downward direction from this point C dash. And what is the scale? Scale that is 3.2 centimeters. So I will take here this red marker and I will draw a line in the form of dash. So this point C dash to I will say here there is a C double dash and I will show arrow towards from C dash towards the C double dash, and it's a I will say radial component of BC, that is A raised to R BC. Now tangential component. So again here is main important thing is that the direction. So we know that the tangential component and radial component are perpendicular to each other. So if I use this protractor and I will draw a perpendicular line to this link C dash to C double dash. So I will draw here one line passing through this C double dash. But which direction that we have to select? So this direction is so much important. So for that we have to refer the direction of this linear velocity for this link. So this linear velocity is also in perpendicular direction to this link BC and it is in the upward direction. So I will use the same direction. So for this perpendicular line I will extend in the upward direction. So I will show arrow and this indicates the tangential component of this BC. So I will say here A raised to T BC. Now exact location of this point B is not known. So again we will move for the link AB. So here link AB, that means here passing through B. Passing through A because A is the fixed point and here is the A dash is there. Now again if we select the radial component, so radial component of BA that we have calculated 0.16 meter per second square. So as per this scale 0.16 into 10, that is 1.6 centimeter. That the scale we have to take. So again radial component is parallel to this link AB. So if I take here one line and passing through this point A dash, so currently I will take the in both the direction I will extend this radial component passing through A dash. Now which direction that I have to select? Now if we observe velocity of B with respect to A is the fixed point about which the point B is moving. So towards fixed point I have to show arrow. So this arrow is in the upward direction. So again I have to show arrow in the upward direction. And what is the scale? 1.6 centimeters. So take here as a 1.6 centimeter. So this distance is very small. And this I will say here is the A dash. So A dash to A double dash. And this A dash to A double dash we have to show arrow and we have to write here A raised to R BA. A raised to R BA. Now in the downward direction we have to remove. Now again in the same way tangential component is perpendicular to this radial component and it is parallel to VB. Now in which direction we have to take? Now here from A dash I have to draw one perpendicular line. But direction if we observe for this VB is in the upward direction. So I will take here one line parallel to this. So if we observe this we have to show arrow in the same direction and here I will write A raised to T BA. That is this is the tangential component. So I will write here A raised to T BA and here I will write A raised to T BC outside. Now here this is the point of intersection. So common point is B. So I will write here as a this is the point B dash. So in this way we will get the radial component and tangential component. Now we will join these end points of the radial and tangential component to get the total acceleration. So B dash to C dash. And here B dash to A dash. So this is the acceleration diagram. Now we will move for the calculation part. So here we have to find out what is the angular acceleration alpha for this link AB and for this link BC. So if we observe, this tangential component of acceleration is required to calculate the angular acceleration alpha. So we can say that alpha for any link is equal to tangential component divided by length of the link. So first we will find out what is the tangential component of this link. So tangential component of AB. So this tangential component for this AB, if we observe, we have to measure vector. This is the A double dash to B dash. And what is the length? That is 16.5 centimeters. So according to scale, if we convert, it is 1.65 meter per second square. Then again, if we move for the next, that is the tangential component of BC, we have to measure the vector B dash to C double dash. And it is equal to 17 centimeter and which is equal to 1.7 meter per second square. So how to calculate this alpha AB? So alpha AB is equal to A raised to T AB, that is 1.65 divided by length, that is 3. So 3 meter here. So 0.55 radians per second square is the answer. Now most important thing is that how to decide the direction. So for that, if we observe, we will refer the direction of radial and tangential components. Now here alpha AB, so for this link AB, this is the direction for the radial component and this is the direction for the tangential component. So now if we observe, this radial component is from B towards A. So if I take B as a center and move the compass in this direction of the tangential component, here is the clockwise direction about B. So I can say that clockwise, its direction is clockwise about B. But if I take A as a center, then this direction is getting reversed. So I will say anti-clockwise about A. Now in the same way, here this alpha BC. So A raised to T BC 1.7 and length of BC, that is 1.5 meter. So it is 1.13 radian per second square. So again we will decide the direction. So here for the radial component, what is the direction? So radial component direction is taken towards the point C. And here this is the tangential component, that is in the upward direction it is taken. So direction is for radial component from B towards C. So we have to take B as a center. And if I move the compass in the direction for this VBC or in the direction of tangential component, then here is the direction, that is, we can say clockwise. So clockwise about B, because here the B as a center. So I will say direction is clockwise about B. And anti-clockwise about C. About C. So we can write any one of the answer, and in this way this velocity diagram and acceleration diagram is getting completed.